This is a recorded webinar about the basics of dust collection system design for battery recycling. It was moderated by Ashley Zook, who's a channel manager at Donaldson Company. She works closely with engineering firms across the United States, and one way that she helps them is through education, hosting webinars like this, as well as in-person lunch and learns. We're going to start off today's webinar by reviewing lithium-ion battery recycling processes. Then we'll get into the four primary components for a dust collection system design: hoods, ducts, collectors, and fans. Participants were encouraged to submit questions into the chat box throughout the webinar, so we finished up with a great Q&A session. Just a heads up that it takes years of education and experience to become an expert in dust collection system design. The goal of this session was to give an overview of the basics for battery recycling.
In case anyone here isn't familiar with Donaldson Company, we have been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first filter for a tractor engine. Today, we are the largest providers of unique filtration technologies, and we excel at producing high-quality filters and parts. We pride ourselves in having a global reach with a local touch. Our world headquarters is here in Bloomington, Minnesota, and we have 55 manufacturing plants and 21 distribution centers around the globe. At Donaldson, we have a strong focus on sustainability. We believe in doing the right thing for our business and community, and we continue to investigate and invest in opportunities to improve our sustainability efforts. Before I introduce our featured speakers today, I wanted to quickly explain on how to engage with us. As you think of questions throughout the webinar, please type them into the chat box, and Chris and Andy will answer them towards the end of the session. If you need to jump off early, don't worry, I will reach out to make sure all your questions were answered. And then during the webinar, they may ask you a question or two that you can respond with a thumbs up or a thumbs down. You can access this at the bottom of your screen with a little face icon. And with that, I am pleased to introduce our featured speakers today, Chris Pro and Andy Winkler. Chris is an industry segment leader for Donaldson. He has been helping customers improve their industrial filtration equipment for over 30 years in the United States, Latin America, and Asia. He has spent time implementing solutions for many plants in the ferrous metals and non-ferrous metals and rock dust applications. He currently is focusing his efforts in the lithium-ion battery market and its associated supply chain from mined materials to finished batteries. Chris holds his bachelor's degree from Rockhurst University and an MBA from the University of Missouri.
Thanks, Ashley. Happy to be here today.
And Andy has been a territory manager for Donaldson Company for the past 7 years and has 30 years of industrial experience in hydraulics and pneumatic system design and application. His time has been spent helping customers solve complex filtration issues by implementing application-driven solutions from Donaldson's array of solutions. And Andy's vast experience in various industrial markets allows him to dig into technical details of a project and arrive at the best total solution for clients. Andy's holds a bachelor's degree from Maryville University in St. Louis, and he resides just outside of St. Louis.
Thanks, Ashley. We'd like to start out by asking about your experience with designing dust collection systems. If you could use the chat box and type the letter in that best aligns with your level of experience, we'd appreciate it.
All right. Looks like they're starting to come in here. We have very experienced, a couple that are new. We have a little bit of wide range and a little bit of experience in the group as well.
Well, great. It's helpful for us to know the experience level of this group. Chris, why don't you kick things off by talking about battery recycling basics?
Thanks, Andy. Lithium-ion battery recycling uses different methods, but everyone faces the same dust problems. Dust control is crucial for the following reasons. First, protecting people. Proper filtration is essential for worker safety, as particulate can be submicron in size. Second, safeguarding equipment. Third, ensuring quality. Uncontrolled dust and contaminant recycled materials can compromise their integrity. And lastly, environment and sustainability concerns. Full disclosure before we proceed, we're experts in dust collection, not designing battery recycling facilities. But I did want to give recognition to some of the professionals and organizations who have helped us to better understand this emerging market. First, NatBat is a nonprofit organization that advocates for collaboration regarding the safe development of advanced battery technology in North America. In this spirit of collaboration, fellow NatBat members Amos Anguil, Bowtree Recycling, Bob Gallion, Dr. Shaolin, and Dr. Wei Kang have all shared their expertise to help us present dust collection best practices for lithium battery recycling. Thank you all. So let's start by talking a bit about how lithium-ion battery systems are constructed. Describing the image on the right, small lithium-ion cells are where the energy is held. They are grouped into modules to boost voltage, density, and capacity. These modules are integrated into larger battery packs, and this forms an electric car's energy source. These three types of lithium-ion battery cells are what will have to be broken down to begin the battery recycling process. From left, first, prismatic cells utilize a metallic or plastic encasement with a rectangular geometry. Then cylindrical cells are like Swiss cake rolls and employ a roll and stack method. And lastly, pouch cells use an electrode fold and stack method to provide a thin, compact, flat shape. Here is a cross section to show the materials that will be shredded and pulverized in the recycling process. The cathode, bottom left, was in a slurry laminated onto aluminum foil. It contains lithium, nickel, manganese, and cobalt. The anode, top right, was in a slurry laminated onto copper foil. It typically is graphite. Those slurries were mixed with a PVDF binder to make them stick. And lastly, there is a separator material that permits electrons to pass back and forth and avoids short circuits. Not seen here, but ever present, electrolyte is a liquid chemical activator, and it is a source of harmful VOCs in the recycling process. After mechanical reduction, black mass is a precursor that can be further refined to the initial elements of lithium, cobalt, manganese, nickel to make new batteries. This slide shows disassembled lithium-ion batteries. The black mass you can see is both fine and sticky due to the presence of the liquid electrolyte. Always wear personal protective equipment and limit exposure. Consider lithium's health risks akin to lead, but less understood due to its relative newness. Also, prolonged exposure is hazardous. Also, when dispersed, this dust could combust. So always test dust for explosiveness to implement proper safety measures. In reviewing stages of recycling, we must consider all companies do this a little differently, and much of it's proprietary. There are, however, many situations during the recycling process that require dust collection. Let's begin with a high-level view of the common processes. Reading from left to right, a typical EV battery life cycle goes from mining, refining, cathode manufacturing, battery manufacturing, use, and end-of-life phase. The diagram illustrates three overarching processes to recover battery materials. Direct recycling, also known as cathode-to-cathode recycling, recovers materials without breaking down their chemical structures. It is an emerging technology and not yet broadly deployed. It creates airborne particulate and also requires handling and dust collection. Pyroprocessing, here intense heat, 1,000 degrees centigrade, melts the materials, separating them into various components based on individual melting points. The high temperatures required can be energy intensive, leading to higher greenhouse gas emissions. Additionally, air pollution controls are crucial to capture any harmful fumes or dust generated during the process. Hydroprocessing relies on chemical reactions in liquid-based solutions to extract valuable material from the battery. The first step involves shredding the battery components into a fine powder, which requires dust collection. This process can be less energy intensive than pyroprocessing, potentially leading to lower greenhouse gas emissions. This appears to be the most common of the three processes in use at present. So Here we've put together an example flow chart of a battery recycling facility. First upper left, spent lithium-ion batteries are received. Shredding occurs at the first stage. Low temperature roasting to drive off VOCs through a dust collector. And so that will go to a thermal oxidizer or could be captured with an active carbon absorption filter. Then secondary shredding, magnetic separation to collect any iron or nickel, further reduction via hammer mill, further separation via air. And then in drum sieving, we drive off power minerals, which makes a battery from other separators. And lastly, winnowing to get rid of coppers and aluminums. At the end of our simplified process, we get to black mass, and it takes the route of going to pyroprocessing or hydroprocessing, where at the end, black powder needs to be collected in a super sack.
Hate to interrupt, Chris, but basically anywhere you see a blue dot, that is where there's going to be a transfer point from one level to another. And that represents areas where nuisance dust could be generated.
Ed, thank you and well put. The processes shown on the prior slide generate both dust and fumes. Dusts are often fine, dry, lightweight, but there's often a lot of it. And fumes can be flammable, exposing the facilities to the risk of costly downtime. We're not going to talk a lot about combustible dust in this webinar. It's a pretty complex topic in itself, but we will circle back to it towards the end of the session. For now, just know that it may be combustible. So, to detail the process, we will start at the beginning with receiving of charged batteries. Working with charged batteries would be the equivalent of playing with live bombs. What you're seeing in the video is a small battery for a remote control toy, perhaps. Just imagine the impact if it was a large battery in a vehicle. Not to scare anyone, but this is the energy that needs to be discharged or processed prior to battery recycling. The recycler needs to get the energy out of at the pack, module, or cell level. Obviously, to discharge a battery by draining its power is easier at the pack level, and the power can just be redeployed. But another common method is to use a highly concentrated saltwater submersion to discharge. This is when we have a variety of smaller batteries, perhaps. This method makes an immense amount of combustible hydrogen gas. And per industry experts, hydrogen needs to be diluted to below 4% with inert gas or airflow to operate safely. From here, multi-stage dry shredding systems play a crucial role. As illustrated by this Amos manufacturing system, the battery materials go through multiple stages to be finely shredded. While nitrogen can be used to prevent fires during this process, dust generation is a constant concern throughout. Aside from shredding, loading, unloading, and transfer between stages, this all creates dust. The image in the top right is a quad shaft shredder, in case you all wanted a closer look at what's going on there. For more background, there are two streams of battery recycling: engineered scrap and used batteries. So engineered scrap is a cleaner material that comes from battery manufacturing and lacks hazardous electrolyte found in used batteries. This is engineered scrap that might come from a gigafactory, testing programs, things that are not usable, so they're not activated with electrolyte. This, however, still generates dust in the process. Used batteries pose a greater risk due to the presence of electrolyte, which releases dust and harmful VOCs upon shredding. So here we go through some more mechanical sorting after the shredding. First with screening. Here larger pieces of aluminum and copper can be driven out. Then with magnetic separation, obviously we use magnets to capture any iron and steel components and remove that from the shredded battery. Then in eddy current separation, this uses a moving magnetic field, basically doing about the same. Might be able to start to remove non-conductive materials like plastics and others. And then air separation, air jets can be used to separate materials based on their weight and density. And so we're still driving off the lighter materials like the plastics and non-energy producing minerals. So all of this displaces air, and all of this require dust collection. And some or none can be used in a recycling facility. Both shredding and separating will release VOC from disassembled batteries that needs to be addressed. In laboratories or smaller scale, the solution can involve a carbon filter inserted in a dust collector to scrub this toxin out. In a larger operation, recyclers should consider using a regenerative thermal oxidizer, like the illustration on the right, to eliminate VOCs. Thermal oxidation can require clean, dust-free air to perform optimally and to extend the life of consumable elements. Thermal oxidation equipment has been applied throughout the battery production chain for emission abatement, from material mining to powder processing, anode coating, battery recycling, and component manufacturing. This technology, it can achieve over 99% destruction of VOC and hazardous air pollutants, and it can be a requirement of many regulatory agencies that be used. After removing impurities and volatile organic compounds, the material reaches a black mass stage. This black mass can then be further refined to extract lithium, cobalt, manganese, and nickel, and the key ingredients for the new batteries. The refinement can happen on site of the recycler, or this can be packaged and shipped to facilities that specialize in further processing. Here it is important to focus on containment of the dust as illustrated in the images above. Also note, air is displaced in the packing process and will need to be filtered accordingly. So, from here we could take two paths. First potential path is pyroprocessing. In pyroprocessing, black mass is put through an oven to reduce carbon materials that are burnable. This also forces the release of active materials from the aluminum or copper. Furnace exhaust systems use dust collectors with fabric filters designed for high temperatures of up to 500 F. However, to prevent premature filter housing damage, it's crucial to understand the future gas stream chemistry. This helps establish proper startup and shutdown procedures to avoid acid condensation, which can degrade equipment. Aside from material handling of black mass feedstock material, hydroprocessing should not be a significant source of fugitive dust. This part of the process uses leaching with commonly available acids such as hydrochloric acid, sulfuric acid, nitric acid, and helps precipitate out remaining copper and aluminum. Hydrogen peroxide can also be added to increase the efficiency. Processes like these in practice can deliver 99.9% recovery of key elements that can be recycled into fresh batteries. I'm going to finish up this section by talking about a few of the many important reasons to control the dust generated during the battery recycling process, including safety. Dust and fumes generated by battery recycling can have adverse impacts on employees in the short and long term. It must be controlled. Battery internal components can be adversely impacted by contamination that could lead to malfunction or even worse, thermal runaway in a product down the line. Clean air for protecting the environment and to support sustainable operations. And cleanliness to assure a world-class facility. Hey, Andy, what's in that picture?
Well, Chris, that's money. What you see in the what you see is deconstructed batteries. It's the mass of material that's inside the core, whether it's cylinder, pouch, or whatever the form factor. That's the guts of the battery. That's where all the money-making materials live. And now that you know a little bit more about batteries and how they're recycled, I'm going to talk to you about the basics of dust collection systems for that recycling. What you see here is a diagram of a typical dust collection system. A blower or fan creates an airflow, which is used to capture dirty air with a hood and then convey the material through a series of ducts to the dust collector. There are contaminants that are separated out through the filter media, and clean air passes to the fan where it's discharged to the atmosphere. It's basically a big shop vac. These systems are a sum of the individual parts and are designed based on the characteristics of the dust or fume and various application factors. If one component is poorly designed, the whole system can be affected. In system design, we have two main objectives. We want to accurately predict how much air in CFM that is required to effectively capture and control dust at their point of generation. And we also want to know the total energy and horsepower required to produce those airflows. The publication shown here is the Industrial Vent Guide. It's basically our Bible. This is an indispensable resource for proper system design. The vent manual was written by the American Conference of Governmental Industrial Hygienists. That's a mouthful. Let's just call them the ACGIH, which is a nonprofit scientific organization that advances occupational and environmental health. They offer multiple courses throughout the year on system design using the Vent Guide as their textbook. I myself, and as well as all my fellow territory managers, have attended courses to develop my system design expertise, and a few of our experts here at Donaldson are actually the instructors. If you have any interest in developing your system design knowledge any further, I highly recommend both of these resources. The ACGIH guidelines are considered by most in the industry, including OSHA, as the standard for proper ventilation design. There are a lot of different formulas that we use in system design. My algebra teacher would be proud that even after 40 years, I still use algebra. The most basic and widely applied formula I use is for airflow. We refer to it as Q equals V times A, where the Q is the CFM of the air needed. And in order to get that Q, we multiply the velocity of the air, the V, by the area of the hood or duct that the air is flowing through. This formula is one of the basic building blocks of dust collection systems. We start at the pickup points and calculate using the formula to get the needed airflow for each pickup. The sum will then give us the total CFM needed for the system. This formula is also used when calculating the needed velocity within the ductwork. Throughout the design of the system, we refer to Q equals V times A over and over again. So let's start at the beginning, at the endpoints, with the hoods. This is a critical component that will allow for containment and collection of fugitive dust. A well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control the contaminant where it's released, while minimizing the energy required to do this. When it comes to assessing an existing system, there's a few common mistakes that I see. The wrong style of hood is being used, the hood's not located in an effective position, or you have inadequate airflow at the hood. In my experience with battery recycling, the dust collection system is sometimes connected to a machine or a series of machines with built-in hoods or a simple dust port connection that only require an airflow or static pressure for our design. That's usually provided by the machine manufacturer. When a hood is required, the most common hood style is a capturing hood, which relies on establishing a general airflow pattern into the hood opening to produce a capture velocity at a specified distance from that hood. There are 5 main types of capturing hoods. You can see them on the screen. The most common that we see are the slotted hoods and the tapered hoods. Going back to the image that Chris showed earlier, you can see a few examples of hoods utilized during a battery shredding process. Positions 1, 2, and 3 are built-in tapered hoods. These are designed by the machine manufacturer at specific transfer points. The other blue dots are positions outside of the machine that are often overlooked, but these are areas where fugitive dust often escapes the process. To minimize air volume, the hood must be close enough to the capture point without disrupting the process. We only want to collect fugitive dust and not good product. A hood positioned twice the design distance from the contaminant emission point will need to draw approximately 4 times more air to produce the same capture efficiency. This is why proper design is critical, because more air means larger collection equipment, larger ducts, larger fan, higher horsepower, all of which to add capital and operational costs. When determining the required airflow at the hood, the main design factor is called capture velocity. This is the amount of air required to reach out and grab the dust where it's generated and gain control of it and direct it to the hood and through the duct. The main goal here is to keep the operator safe and keep the particulate away from his or her breathing zone. The chart shows a general rule of thumb for capture velocities. It ranges from very low levels for very light floating contaminants to high velocity sprays of dust. Whether you're designing hoods or relying on machine design, we want to avoid airflow extremes. Too much airflow at the hood or pickup point may mean you're picking up good product rather than just nuisance dust. And since more energy is required to move more airflow, this could lead to higher than expected operational costs. Insufficient airflow at the hood could require additional housekeeping measures to be implemented, and depending on the dust, may lead to an increased risk of exposure.
Thank you, Andy. Sorry to interrupt you. I just wanted to remind everyone to make sure you submit your questions in the chat box. I see a few in there, and Chris and Andy will address them towards the end of the session. Andy, why don't you talk to us about duct design?
No problem, Ashley. And now back to the regularly scheduled program. Once we design the proper hood to capture the contaminant, the goal is to move the particulate to the filtration system through a series of ducts. A properly designed duct system should pull the minimum airflow required at each hood, should maintain the velocities required to move the material through the duct to the collector, and keep the material suspended in the airstream. And you should do this using the least amount of energy as possible and minimize any wear and tear on the duct components. A few common mistakes that I see quite often are the wrong duct type, the wrong size, and the system being unbalanced. The minimum duct velocity is a critical design factor. It's the lowest velocity where all contaminant will remain suspended in the airstream. If you go below this velocity, dust could settle out within the ducts and cause other safety issues. Duct lines, no matter the size, must be full of air at the designed conveying velocity to avoid settling out. For many of the light dust generated in battery recycling, the industrial ventilation manual lists the minimum at 2,500 to 3,000 feet per minute. However, 4,000 feet per minute is the minimum duct velocity if the dust is combustible, which it typically is when we're talking about battery recycling. So you're going to see duct velocities in that 4,000 to 4,500 feet per minute range. If the duct velocity is too high, it'll require more energy to move the air through the duct. Ultimately, this could impact the size of the system fan, as well as create issues such as increased noise, abrasion, or wear and tear. Having a balanced system is one of the most important aspects to an effective dust collection system. It ensures you're pulling the required amount of air from each hood. A lot of issues have been created in existing systems when the process owner goes to add an additional leg and doesn't account for the ramifications downstream. Give me a thumbs up in the chat box if you've ever seen this happen in your experience. You design an amazing system, you find out later, the process owner went and changed something, and then you get a call saying your system isn't working right.
All right. Looks like we had a couple thumbs ups here. They're coming through.
All right, well, we see this quite often. Most of the time, these additions were not planned and the system can become unbalanced. If you know a customer is going to be expanding their process in the future, there are ways to design future lines into the system so they don't have to sacrifice performance. But if a customer needs to add a line to an existing system, call in a professional help. Don't just do it and expect the system to work. Just a few quick pieces of advice when it comes to duct type. Rectangular duct is commonly used in HVAC applications where you're moving air only. We don't want to use this in industrial applications because dust settles out in the corners. It's okay for the clean air side. When specifying industrial duct systems, make sure to call out round, heavy-duty industrial ductwork. Most collection systems and applications will use class 2, 3, or 4 ductwork, which are designed to the SMA CNA standards. Spiral duct, one of my least favorite types of duct, tends to leak air and could impact your design of airflow by about 10%. If used outside, it also provides a prime source for water to enter the ductwork and get into the dust collection system. So spiral duct is not recommended. May be the cheapest, but it'll cost down the road. And be aware that although flex duct allows employees to modify the physical hood location to fit their processes, it requires significantly more energy than traditional hard ducting. So if you're going to specify flex ducting, we recommend minimizing it as much as possible. Personally, I think the dust collector is the most important part of the dust collection system. You can have everything else right in the system, but the wrong collector can cause unnecessary issues. The overall objective of a dust collector is to deliver sufficient efficiency while operating in a predictable, stable, and cost-effective fashion. A lot of mistakes that we've run into include the wrong filtration technology, incorrect sizing, either being too aggressive or too conservative with the air to media ratio, insufficient dust removal capacity, and poor installation. I'm going to start with our cartridge collector. They are typically smaller and have a lower initial cost than a baghouse. They're best for low to medium dust loads and fine uniform dry dust types, like those found in battery recycling. They are continuous duty, so they don't need to shut down in order to clean the filters. They use the plant's compressed air, and they use small, easy to handle cartridge filters. Pictured here is our Torrent Downflow Evolution, or DFE collector. This is our flagship collector, and the one that I use most frequently in battery recycling. I think it's kind of fun to see where we got to today's DFE collector. This is a wonderful slide that shows the evolution of our cartridge collectors. Way back in the 1970s, while listening to ABBA, we basically took a baghouse and replaced the bags with cartridges. It was okay, not great, and unfortunately, we still have manufacturers doing this same design that we did back in the 70s today. Next, we moved the inlet to allow gravity to assist us and bring the dust to the containers. Again, a step forward, but improvements can always still be made. We made a huge step forward in the 80s. We rotated the filters and allowed gravity to help even more. Combined with our state-of-the-art airflow testing, we were able to see a dramatic increase in the ability of the collector to remove dust. In 2014, we introduced the DFE, which moved the air inlet to a space behind the filters that allowed the dirty air to flow past the filters to the bin before hitting the filters at all. Doing this, we were able to do more with less filter media that lasts a lot longer. Just like cartridge collectors have evolved, so have the filter medias. Nanofiber was introduced by Donaldson in the 1980s. The red dots on the image are representative of a single dust particle. As you can see, the cellulose media on the left has many more areas within the media to allow particulate to load beyond the surface of the media itself. And both large and small particles can embed deeper and deeper into the media. It's called depth loading, and it's not a great situation. However, dust cannot easily get out from beyond the surface of the ultraweb nanofiber in the image in the middle. This allows for surface loading of the filter media, which improves filtration and cleaning efficiency. It's a lot easier to pulse fine dust off the surface of the media rather than from deep inside. The most common filter that I recommend for our battery recycling is Donaldson's UltraWeb, which is a MERV 15 cartridge media. It filters down to 0.3 micron in particle size. We have multiple options beyond the standard media for different types of dust and media coatings for fire resistance, dust release, static dissipation. Most battery recycling facilities are large, and the dust collector is located indoors and exhaust is returned into the facility. I recommend a HEPA filter as an after filter frequently. It's 99.97% efficient, but it's not uncommon to also see our ULPA or ultra low particulate air filters that have a greater efficiency of 99.999%. But if you have VOCs in your airstream, I think I saw a question talk about this or ask about this earlier. You have VOCs in your airstream, you should consider a carbon after filter instead of HEPA. HEPA will not be able to filter out VOCs, but a carbon after filter can. Sometimes cartridge collectors aren't the best option, particularly in the process producing agglomerative dusts, which are sticky and they bind together. If there's moisture present, or if the dust loading is really, really high. In these situations, we look at what we often call our workhorse or our problem solver collector. It's called the Dalomatic. The Dalomatic uses an envelope style bag made from different medias based on the application. This envelope style bag, when the compressed air is shot into it, it creates a very violent pop, dislodging the material from it. It's a lot like blowing into an envelope. It really pushes those sides out and gets a lot of movement. This is used very successfully in difficult to remove dust. For example, I've used it in concrete plants by the Mississippi River where the concrete is hardened on the bag and we're able to get the material removed from it. When designing a system, the very last thing we do after completing all the airflow calculations is we select and size a fan. A critical component of fan design is static pressure. It's basically the resistance that the airflow must overcome due to the system components. It's expressed in inches of water gauge or water column. And when we design a system, we calculate the total system static pressure so we can size the fan properly. Here's an example from a recent system that we designed. The hoods totaled 1.5 inches of water. The ductwork, including straight runs of duct, elbows, branch entries, totaled about 2.5 inches. The filters in the collector totaled 6 when completely dirty. It's worst case scenario. And the filter to the fan ducting was about 1 inch. So the total system static pressure for this particular project was about 11 inches worst case scenario. Our fan is like the heart of the local exhaust system. It has 2 job responsibilities. First, it has to deliver the necessary flow at the required static pressure to drive the operation of the system. And since many dust collectors can operate with clean or dirty filters, the required airflow is often has to be maintained over a range of static pressures. Secondly, the fan you select should be able to maintain the appropriate energy efficiency at an acceptable sound level. For example, non-material handling fans located on the clean side of a collector are more efficient than material handling fans on the dirty side of the collector. Fan challenges generally fall into 2 categories: poor fan selection and poor fan installation. The fans are sized based on the system's total static pressure and the required airflow. For example, let's say I need to size a fan for the example I gave you earlier, 11 inches of water at an airflow of about 9,000 CFM. We use the static system pressure of 11 inches, mark there you go, with an airflow of 9,000 CFM. And when those line up, we land actually between 2 sizes, the TBI 25 or torque backward incline and the TBI 30. When the lines intersect in between 2 fan curves, like they do here, we generally select this larger size fan since you can always damper that back. So in this case, I would select the TBI 30. Chris, do you want to talk briefly about a few other design considerations before we answer questions?
Absolutely. So toxic battery dust necessitates proper plant and worker protection when handling filters and controlled dust. As seen above, recycling facilities should consider utilizing an adapter. We call it a bag in, bag out process for handling dirty filters. And I would recommend putting this in your spec. Bag in, bag out allows the operator to load and unload filters into the dust collector while minimizing the dust exposure to the facility. And we also have options for bagging out the collected material below the hopper. As I mentioned earlier, the dust generated during the battery recycling process may be combustible and pose a fire or explosion risk. I'm sure most of you are familiar with the fire triangle shown above here. Fuel, oxygen, and a source of ignition produce fire. When the source of fuel, which is our dust, is finally dispersed in the manufacturing process, it can lead to flash fires. When that dust is then contained within a dust collector enclosure, the conditions are right for a dust explosion. We know this can be pretty complex and a complicated topic. On the slide, you can see some different mitigation options that process owners can consider, such as flameless explosion vents and inlet isolation. Depending on the application, the authority holding jurisdiction, and the process owner's risk tolerance, you may use one of many different options. But please give us a call and we'll be able to provide you with expertise needed to make the best selection for the situation. The last consideration I wanted to mention is how technology is being used to monitor dust collection systems. Donaldson has developed a device called iCue to make dust collectors smart. iCue delivers real-time process data, automates alerts for potential issues, and generates historical reports, all at no additional cost. It's a great way for operators to manage and track regulatory compliance information and troubleshoot dust collection issues more efficiently, such as when the filter should be changed before they eventually fail. We get that designing dust collection systems for lithium battery recycling can be complicated. Each system and facility is unique, and there's a lot that goes into it. But that's what we're here for. We've sold countless dust collection systems around the world, and we have a vast network of territory managers and authorized dealers to provide local support in your market, and we're here to help make sure we get it right the first time.
All right, thank you guys, everyone. We're going to be finishing up here with some Q&A. Chris and Andy, you can turn your cameras back on. Just a heads up to everyone who has attended, you will receive an email that includes your PDH credit. If you have any additional questions, my contact information is on the screen. Also, we're going to put in a link into the chat box for our webinar that has a few of our recorded webinars, along with the form you can fill out if you're interested in an in-person lunch and learn or a customized webinar for your team. All right, here's to our first question. We typically assume that the SOC of less than 30% reduced this risk to thermal runaway. What state of charge is needed to start the recycling process?
Okay, I'm not a battery recycling expert, but from reading their information and talking to them, I believe that figure is 0. I don't think we want any charge unless we have a process that can handle some charge in the batteries. I'll be happy to research that a little bit more with you offline, but that's my understanding of that at this point.
Okay. Next one is when you shred batteries, is it submerged in anything or shredded in air?
That's a very good question. So for the purposes of a dust collection webinar, we were talking about dry shredding, but there is water processes that add water to the process of the batteries to mitigate any fires or some other solutions. So there is a wet shredding. That produces a different characteristic of dust, maybe a moist dust that needs extra firepower and a dust collector to pulse that stuff off. But that's what I can say about that one.
All right, next question here is due to hazardous products used in manufacturing of battery separators, how does a dust collection system work in addition to the toxic fumes?
So that is, I believe, a polypropylene, polyethylene product, not really in the vein of manufacturing batteries, but more of a chemical plastic process. Dust collection and mist collection could be employed with that. Like I said, case by case. We'll be happy to look at that in depth offline for you if you want to send us more details.
And Chris, Jamie put this in right before you started talking about the RTOs. So a lot of the toxic fumes that we see, we run through after the dust is taken out of the collector or out of the airstream by the filters. The fume-laden air, because we don't take out VOCs and fumes, will go and feed into the RTO, or we can see that going into a carbon filters to collect that. However, if you're talking the toxic fumes, feed that to an RTO, but it has to be very clean, almost 0% dust in that air. Those RTOs can throw errors and shut down.
RTO is regenerative thermal oxidizer, correct?
Correct.
Yeah, okay.
All right, on to the next one here. It says, what is the compressed airflow and pressure requirements for each type of filter for cleaning?
Well, for our DFEs, the larger systems that are 2 filters deep, that's in that 90-ish PSI pressure for the cleaning system. And depending on the size, it could be 8, 9 SCFM per filter, or not per filter, but per collector. Again, that depends on how many total filters we're seeing in it. For the Dalomatic, we're in the 60 PSI range for that type of envelope style filter. If we're talking a standard baghouse, that could be as low as 7 PSI, but that's more of a continuous pulse. So again, those are some very general thoughts or very general pieces, but it really depends on the actual application.
All right, next one says, any recommendations if there is a need for a booster fan upstream from the dust collector?
If there's a booster fan needed upstream, there is a design issue. We should be able to pull everything downstream to the dust collector with the one fan. I've got a couple of applications that the machine has a fan in it that pushes towards the dust collector, and we can use a type of slip flange or slip duct that will allow the extra air to be dissipated within that. I don't often see needs in a properly designed dust collection system for a booster fan upstream of the dust collector.
All right, the next one we have here is, are there any special material changes, selections to ensure that the dust doesn't come in contact with reactive material?
You know, the only things I can say is I probably need to know more before being specific, but you know, nitrogen gas is employed to mitigate combustibility of battery materials as it goes through, and you know, just discharging the materials as much as possible.
Okay. It says, regarding black mass being potentially combustible, have you seen data that indicates black mass that has electrolytes, or sorry, I'm murdering that word, and VOCs properly removed is a combustible dust per NEC guidelines?
So first and foremost, and there's somebody else who's got a question down the way there. You can buy black mass and get an MSDS sheet on the product. So a lot of people can sell black mass, and their contents vary based on the batteries they recycled. But you know, the certain way to address this is to test your dust, get the KST value, then you understand what risk you're dealing with. You know, some of these materials may not be the most combustible. Ground up really, really fine into fine particles and dispersed in air, it could be very combustible. but a proper dust test will tell you that, and it's not that expensive. And then you know how to design for it.
And the process owner is responsible for that test. So there are many wonderful labs out there that can do the test. I personally use one out of Chicago called VOCs. They can give you a simple go, no go test, and they can also give you a how bad is it if it is a go. But again, the process owner is responsible for that dust hazard analysis. I have a customer that has done 3 tests on their mass, and all 3 tests have come back that it's not combustible. Then there's another customer who's done a few tests and their dust comes back combustible. So it really is up to that individual process owner, and they're, as Chris said earlier, each process is different. At certain levels, at certain stages, there is going to be some combustibility. Where that is in your process, that could be different. So again, as the process owner, you're responsible for that.
All right, the next one is there a general rule of thumb for maximum distance ducting can travel from collection point to dust collector?
There is not a rule of thumb, because a properly designed system can go thousands and thousands of feet. We have systems out there that the ductwork is a labyrinth, a maze, and quite honestly, trying to figure it out half the time when you go into an old system can be quite daunting. But if it's properly designed, we can run that as long as we have the static pressure calculation and we've calculated the dust, the airflow that's needed, and the ductwork is sized correctly. So if I take a 4-inch and add a 4-inch, that ductwork now needs to be, the main ductwork now needs to be 6-inch in general. Every time you add, you have to adjust that duct to meet the airflow needed and the velocity needed. So there is no rule of thumb if it is designed properly.
Okay, next one here is, are cartridge dust collectors capable of handling plastics?
The answer is it depends. Yes, they are, but it depends on the state. If it is a ground plastic, is it just the general dust? I have different coatings on different cartridges that we can use, but yes, we can do plastics, and no, we shouldn't do plastics on it. So again, the answer is it depends on the application. I'm working on one right now that is, the air volume is so high that we went to a baghouse, but we're using a pleated bag, which is basically a cartridge in the shape of a bag that hangs on that. And it's a spun bond, so it's got a coating on it which will not allow, in that case, the little barbs of plastic would not get into the cellulose media to stick to it. I've got different coatings, I've got different filters I can use. I can make it work, but it really depends on the application.
All right, what is the minimum dust size in microns in the typical battery recycling process?
So I hear the term nanoparticles thrown around a lot. You know, I can't say without actually taking a look at the dust and do a particle size distribution analysis to know exactly what you're going to get. But let's just say our filters, HEPA filters, go down to like 0.3 micron, which is the equivalent of the smoke from a cigarette.
Okay, next one here is how to design a future-proof dust collection system. Do you need to over-design the dust collection system at the beginning to satisfy future expansion purposes?
If you know that there is going to be expansion happening, then what you need to do is learn about the future process. If it is going to be, yes, we're going to add in a whole nother machine over there. It's going to require 4 6-inch inlets, as well as some general maintenance areas for inlets. You can create a virtual branch and have an open, I usually put a slide gate on there, bleed in filter to allow for that future leg to operate. So for example, like I said, you have this future machine going in. I just have a Y branch at that point where it's going to be, and I have an opening there, so I'm able to suck in that air. I could shut that down and taper and use like VFD and pull the fan speed back, but then I run the risk of having dropout in the ductwork. So we always have to go back to maintaining that back to that Q equals V times A. We have to maintain that velocity to keep things in the air, and whether that's bleed in air for that future piece or VFDs, that is where you look at the scenario on how to future-proof it as much as possible.
All right, and it looks like our last question here is, should early condensation effects be considered? Condensation of electrolyte solvents being released during shredding?
Yes. So anytime you introduce moisture into the air, it depends on the level of moisture. Anything over, say, 10% moisture, we need to look at the filter media. We may need to go with our spun bond media, which has more resilience to moisture and will allow things to drip off, if you say, or for example. But then we can also look at our dolomatic. So our dolomatic, we have that condensation, we get that wet sticky dust into the collector. Once that dries, that dolomatic is able to knock that stuff off. So yes, condensation effects need to be looked at during the process.
All right, well, thank you, Andy and Chris, and thank you everybody who's joined today. Like I said, you will receive an email with your PDH credits after, but thank you and have a great afternoon.